I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll briefly discuss about the topic hyperparameter tuning. First, we'll see the introduction to hyperparameter tuning. The hyperparameter tuning involves finding the best setting for parameters. In the sense, hyperparameters are external configurations that guide how a machine learning model is trained. Unlike model parameters which are learned from the data during training, like weights in neural networks, hyperparameters must be set manually or through an automated search strategy. Their correct selection can significantly impact a model's performance. Next, these values are set before training, not learned from data. That means hyperparameters are not learned through optimization but rather set in advance. This means we must guess or test what values are best, making it necessary to explore multiple combinations using tuning techniques. And say, for example, if we are taking the example learning rate, batch size, number of layers, and dropout rates. Common hyperparameters include the learning rate, how quickly the model updates. Batch size means number of samples per gradient update. Number of layers means depth of network. And dropout rate means how many neurons are randomly turned off during training to prevent overfitting. And it is important for maximizing model accuracy and generalization. That means tuned hyperparameters can reduce on both training and validation data sets, leading to model that generalizes better to unseen. And poor tuning may lead the finally poor tuning may lead to high bias. That means underfitting or high variance means over fitting. The poor tuning leads to that is the poor tuning leads to underfitting and overfitting or slow convergence. In the sense, if the hyper parameters are set improperly, the model may not learn patterns in the data, may memorize noise, or may take too long to train effectively, all of which compromise the model's performance. Next, objectives of tuning. Types of hyperparameters. The model related means number of layers, hidden layer units, and activation functions. These hyperparameters determine the structure of the model. For example, more layers and hidden units allow the model to learn complex features, but they also increase computational cost and risk of overfitting. And activation functions like ReLU, sigmoid, or TANH also significantly affect learning behavior. Next, training related, that is learning rate, epochs, and batch size and optimizer. In this sense, these settings control how the model learns from data. The learning rate decides how large each parameter update is. Epochs determines how much times the model passes through the training data. The batch size affects the stability and the speed of learning. And the optimizer, example SGD, stochastic gradient descending algorithm, controls how gradients are used to update the model. Next, regularization related means regularization hyperparameters prevent overfitting by penalizing model complexity. L1 and L2 add a term to the loss function based on the magnitude of weights. Dropout randomly disables neurons during training, forcing the model to learn robust features. Finally, the different models require tuning different sets of hyperparameters. For example, a decision tree requires maximum depth and minimum samples per leaf, While a neural network needs learning rate, number of layers, and optimizer settings. Therefore, tuning is always specific to the algorithm. Next, objective of tunings. The goal is minimize the validation loss or maximizing accuracy. The objective of tuning is to find a combination of hyperparameters that yields the best performance on the validation test. This ensures that the model is not just memorizing the training data but can also generalize to new unseen data. And the second one is optimizing performance. We focus on the validation set during tuning to avoid overfitting to the training set. This helps ensure that the model performs well when deployed in real world situations where it encounters new data. And we have to use this objective function minimum of L value of theta comma that's a lambda. The hyperparameters lambda, the Turing parameter focuses on finding the best lambda that supports this objective. And finally, they use separate training, validation, and test dataset. Splitting data ensures a fair evaluation. Training data is used to fit the model. Validation data helps tune hyperparameters, and test data evaluates final performance after tuning. Next, common hyperparameters in deep learning. Learning rate. That is too high divergence. Too high means divergence will occur, and too low means slow training. The learning rate controls how much model weight changes during each update. A high value may cause overshooting and instability, while a low value slows down convergence and may get stuck in local minima. Next, batch size. Smaller batch sizes provide more noise in gradient estimates, which may help generalization but slow training. Larger batches use more memory but can lead to faster training and smoother updates. Epochs, the total passes through the data sets. One epoch means that every sample in the training set has been seen once. The number of epochs affects training duration and convergence. Too few may underfit, too many may overfit. Next, dropout rate. Dropout disables a fraction, that is P, of neurons during training. This forces the model to rely on multiple pathways and avoid overfitting to particular patterns. Hidden units and layers control models complexity and capacity. More hidden units and layers increase model capacity to learn complex patterns. However, it also makes the model prone to overfitting and more difficult to train. Next, grid search. Uh, Test all combinations from the predefined set of values. Grid search systematically goes through all possible combinations of hyperparameters in a specified grid. It's exhaustive, but it is exhaustive, but computationally expensive. And if you are taking the example, the learning rate and batch sizes, etc. By training every pair, grid search ensures that all possible possibilities are considered, which is useful for smaller search spaces. And it guarantees best result with a grid. If the true best hyperparameter values are within the grid size, search will find them. This makes it reliable for low dimensional tuning. It has got some drawbacks also. Computationally, it is computationally expensive, especially with many parameters. As the number of parameters and the choices increases, the total combinations grow exponentially and making grid search impractical for large problems. Next, random search. In this case, it selects the random combinations of hyperparameters. Instead of testing all combinations, random search picks combinations randomly. It is a faster alternative to grid search, especially when not all parameters are equally important. And the next point is research has shown that in many cases, only a few hyperparameters significantly affect model performance. Random search is more likely to find them efficiently. And the next one is because it avoids exhaustive testing, random search can cover a wide area of the search space using the same computational budget. Finally, in spaces where parameters can take continuous values like learning rates, random search allows more diverse sampling than grid search. Next, Bayesian optimization uses of a surrogate model to estimate performance. Bayesian optimization uses models like Gaussian processes to predict the outcomes of untested hyperparameter settings. This makes it more sample efficient than random or grid search. Next, it selects the hyperparameters using acquisition function. An acquisition function balances exploration and exploitation by determining where to sample next. It selects hyperparameter values that are promising yet not sampled. Next, balances exploration versus exploitation. It explores new areas, uncertain but possibly good, and exploits areas known to work well. This adaptive strategy often finds better results faster. Next, commonly uses Gaussian process. Gaussian processes provide a probabilistic estimates of performance for untested hyperparameters. This helps guide the search intelligently and efficient for tuning expensive to evaluate models. Bayesian optimization is ideal when model training is costly as it minimizes the number of training sessions needed to find optimal setting. Next, cross validation in tuning. Cross validation ensures that hyperparameters ensures is not biased by one specific train or validation split. This leads to more reliable measurement. So that only we are going for k-fold CV. Cross CV means cross validation. So in this case, this equation here we have divided the data into k folds, train on k minus 1 folds, validate on 1. Average performance CV score, cross validation score is given by 1 by k, summation I is equal to 1 to k, allow value of I. So this equation gives the average validation of a summation divided by k. So that we are calling it as average. Loss is, this gives the average validation loss across all folds, providing a robust estimate of model performance, and it reduces the bias in validation result. Cross validation ensures that every data point is used for both training and validation, reducing the risk of selecting hyperparameters that overfit to a specific split. And by averaging over multiple data partitions to chosen hyperparameters are more likely to perform well on unseen data. Next, practical tuning tips and use log scale for learning rates 0.0001 to 1.0. Learning rates vary widely in effective ranges. Using a logarithmic scale ensures better coverage of small and large values without clustering around arbitrary intervals. Next, start with a wide range. Begin with the coarse tuning to identify promising regions that refine the search around them for fine-grained optimization. Tune few parameters at a time to reduce search spaces. Next, focusing on a third point, the focusing on the most impactful one helps manage complexity. Next, use early stopping to prevent overfitting. Early stopping halts training when validation performance stops improving, saving time and avoiding unnecessary training. And automate with the tools. Modern libraries offer automated tuning with the random search, Bayesian optimization, and more. They handle resource management and performance tracking. Coming into the summary, hyperparameter tuning boosts model performance. That means tuning ensures that model is learning efficiently, and generalizing well, which is essential for practical deployment and critical for deep learning. The second point is the critical for deep learning ensemble method and SVMs. Different algorithms depends heavily on hyperparameter choices. Deep learning models in particular can perform very poorly without good tuning. Main methods are grid search, random search, Bayesian optimization. Each method has strengths and weaknesses. Grid search is exhaustive, random search is faster, and Bayesian optimization is intelligent and efficient. Use validation and cross validation to evaluate tuning. Always validate tuned models on separate data to ensure performance holds. Cross validation gives a comprehensive performance view. Proper tuning leads to faster, more accurate, and more reliable models. Effective hyperparameter optimization results in models that not only perform better but also train faster and behave more consistently across datasets. Hope everyone understood about this simplest topic, namely hyperparameter tuning. The remaining things we'll discuss in the next lecture. Thank you.